discuss the internal energy, enthalpy, and the specific heats of ideal gas. So from ideal gas, we know, VP, this is equal RT, right? We know this P is, it is actually the the pressure. V is the specific volume. So V is a specific volume. R is gas constant, and T is temperature, right? We know all of this. So yeah, so when it is an ideal gas, then we know this expression, this relation. So now, if you look at this arrangement, actually we're trying to understand the internal energy, enthalpy, and the specific heats. So Joule in 1843 did some experiment and showed the internal energy U, okay, it is actually the function of T. So this is Joule showed experimentally in 1843. So how he did this experiment? He just took a chamber like this. It is filled with water. He also used to submerged tank. So this is, let's say, first tank and the second tank. He connected these two tanks by using a pipe and put a valve here. So the one tank, it is actually filled with the air at high pressure. So it is the air at high pressure, and other is evacuated. So it's empty. So when this system is in thermal equilibrium conditions, so then what he did, he just removed this valve and allowed all of this air to move to the other empty tank through this pipe. So once the air passes from this tank to this other tank, so until the pressure equalized in both tanks. So what Joule found, when all the air that passes through this tank to the other tank, so what Joule observed, that the temperature it is constant. Temperature is not changing, no heat transfer happened here. So he's found no temperature change in this air and the water. So what happens, that means no heat is transferred to or from the air. So that means no work actually done in this case. However, we can see the volume changes and the pressure changes from this high pressure to when the air transferred to the other tank. The pressure changes or the volume changes, but temperature is not changing. So that's the observations from this experiment Joule found in 1843, and what he concluded, that the energy inside this tank, it is actually the internal energy. So Joule concluded that the internal energy, this is actually the function of temperature. Okay, this is function of temperature. So it is not as a function of the volume and the pressure. So in this case, you can see the volume was changing, the pressure was changing. So it was his observation. Okay, so it is just function of pressure. And we are trying to understand the internal energy, enthalpy, and the specific heats and the relations between these three. So we know the definition of the enthalpy, and so the enthalpy, we usually use the term Hayes. So Hayes, it is equal the internal energy plus the pressure and the volume B. So we know this is actually the definition of the enthalpy. And from ideal gas equations, we know PV equal RT. So if we substitute this value here, then it will be kind of like this. You see, U plus RT, because we substitute PV, it is equal RT, right? So we got Hayes, it is equal U plus RT. So what we can say, guys, from here, Hayes, this is enthalpy. Hayes is enthalpy. And U, it is function of T. Can I write it like this? It is U function of T, it is R, and this is T. So if you look here, this is actually function of T. This is temperature. This is also temperature. And R is the gas constant. that means we can say actually enthalpy, it is also a function of T. Okay, what we said here, the internal energy, this is the energy which is only the function of temperature. Here we found the enthalpy, it is also the function of temperature. So that's the relation we developed from the internal energy and from the enthalpy definition. So it means the haze and U, it depends on temperature, only on temperature, and not for pressure or a specific value. So as it depends only on temperature, similarly the specific heats at constant pressure and specific heat at constant volume, Cp and Cv, it mostly depends on temperature only. So it also depends on temperature only. So what we can write, guys, we can write it like this: the U, it is function of T, the haze, it is function of T, the Cp, it is the function of T, Cv, it is also function of T. So all of this, it is actually the function of T, depends on only on temperature. So if we know the partial derivatives actually for ideal gases from I discussed earlier. So we know the specific relation Cv, it is equal du dt, and this is V, and the Cp, we know it is equal d haze dt p. Let's say this is equation 1, this is equation 2. We know these equations for Cp and Cv. Here we found Cp is only function of temperature, Cv is only function of temperature, but we know this. So what we can write, guys, from this expression, if we do some cross multiplication, let's say if we put 1 here, then can we do some cross multiplication like Cv dt, it is equal du? Yes, we can write that. We can write, okay, du, it is equal Cv dt, and from this expression we can say d haze, it is equal Cp dt. So d haze, it is equal Cp dt, just the cross multiplication. So from here we found Cp, it is Cpt. So then we can write it like this: it is Cp t dt. Here we can write Cv equals Cpt. So let's say Cv t dt. So this is actually the differential form of the internal energy and the enthalpy, right? We got actually the differential changes of the the internal energy and the enthalpy. We're trying to correlate the internal energy, enthalpy, and the specific heats. So this is the specific heats, this is the internal energy, right? Yes. So now if we have a system, the process, the state 1 to state 2, if we want to calculate the the change of the internal energy or the change of the enthalpy in an ideal case when during a process. So if we really want to calculate the change of the internal energy or change of enthalpy for an ideal gas during a process, so what we can do, we can do some integration. So we can write, let's say for this internal energy, we can write this change delta U, it is equal for the process, let's say this is process 1, process 2, that means the internal the difference U2 and E1, we can write it is equal the integration of 1 to 2, and then this one Cv t dt. And similarly for delta haze, we can say it is haze 2 minus haze 1, it is equal 1 to 2, we can write it is Cp t dt. So this is actually the you can see the relations here. We found d delta v, so this is actually not delta v, delta u. So this internal energy, it is we can calculate the rate, the change of the internal energy by doing this integration between these two processes, C1 and C2. So we found a relations between these two, internal energy and the specific heat, enthalpy, and the specific heat and the temperature. So we can easily do all of these calculations by using this formula. So during the lecture I will discuss a bit more. Actually, I'll try to discuss what happened at low pressure. I'll try to discuss the behavior, the ideal gas constant, pressure, specific heats for low pressure and temperature. So I will discuss those curves and I will try to discuss some more equations. So here what we did, guys, we said actually the ideal gas equation, and we found from the Joule experiment that it is the internal energy, it is only the function of temperature, and then we use the the enthalpy definition. We substitute all of these values. We also found the Hayes it is also function of temperature, and CP we found this is also the function of temperature, and then we just tried to drive this. So this is very simple calculation. We will use all of these equation you see again and again throughout the semester for the CP. Yeah, so I think that's it, and we'll discuss more in more details during the lecture.